Okay, so my plan, if you read the email I sent out earlier today, the plan is to finish chapter 2 by Thursday and test you on Friday. We've only got a section and a half here to really finish up, and the next section really is just a continuation of this one. So we're going to spend about 4 days on this. And in actuality, guys, this is just an introduction to something that we're going to be doing for several months. Okay? We're going to start doing some proofs. Okay? The logic behind doing these proofs is we should be able to start recognizing and understanding the why that is behind mathematics, the why we do some of the stuff we do, what allows us to do some of the stuff that we do, and be able to develop an argument for why something is true. Okay? The phrase that I've heard, or that I've used over and over again, you guys heard me say, the monkey see, monkey do type thing, or be a robot. Don't want to be a robot in mathematics. I'm fighting this right now with my college students. Is I give them a problem, and they say, well, I've seen this in class. I've seen Mr. Fay do this. We can do it the same exact way. And I give them another problem, and they say, I'll do it the exact same way. And I give them a third problem that has a very similar structure. But if they approach it as a monkey see, monkey do, or being robotic, and they do just like they did on the first and second one, they will miss the third one because they're not thinking. Okay? So this gets us thinking about mathematics, thinking about logical progressions of mathematics. If you can do this, which every one of us has the capacity to do this, okay, it will make your mathematics understanding so much stronger, and then it will allow you in all fields of mathematics to be so much more efficient and successful inside maybe the arithmetic type problems. Okay? But 2.5 is about reasoning in algebra and geometry. Okay? You see there in quotes I got, why do we know what we know about something? Okay? You all had arguments with your parents before, right? Or with one another, with peers, okay? And you always try to, say why. Maybe, Landon, you're a Falcons fan, aren't you?
Yeah.
So who do the Falcons play this week? Titans, they get beat by them? Yeah. So let's say, I don't know what the schedule is. Let's say the Falcons, have they beat anybody this year?
The Eagles.
The Eagles, okay. So let's say, the Falcons beat the Eagles, and the Eagles beat, let's say the Eagles beat the Redskins. So your argument now is that because the Falcons beat the Eagles, but the Eagles beat the Redskins, the Falcons, when they play the Redskins, the Falcons are going to win, right? That makes sense? Everybody does that, right? You guys, we do that in high school sports. We beat Elida, okay? So when we play somebody that Elida beat, we should beat them, okay? We do that all the time, and that's an argument. That is a deductive argument, okay? We're actually using kind of what we call a transit property doing that, okay? But we want to when you have an argument with somebody, you want to make sure that you have a valid argument, okay? So that's kind of what we're going to get aligned with, or try to get all this information learned here so we can start doing that, okay? A lot of the properties we see today, guys, are going to be things that you've already dealt with, okay? Things that you already know. But they're going to be essential for us inside our proofs, okay? These, 8 properties here, okay? 5 of which you are very familiar with. 3 of which I've highlighted, maybe you've never heard before, okay? I'm going to kind of walk you through the ones that we're going to use the most here, and they should be obvious. A lot of our math concepts as standalone concepts, all by themselves, are common sense things, okay? For instance, the addition property. All of these say we're going to start with 3 things, A, B, and C. And if we see A, B, and C, they are real numbers, okay? Meaning anything off the number line you want to choose. The addition property of equality says if A equals B, so you're going to take two of these three numbers, and you're going to make that requirement. You're going to say that the A and B you chose are the same. So let's say I chose A to be 3, therefore I got to make B 3, right? So if 3 equals 3, then I should be able to take 3 and add to it 7 on the left-hand side. And if I do the same thing to the right-hand side, so I took A and added C to it, which in this case C was 7. And I took B and added C to it, and in this case C was 7 again. I should still get a true statement, right? Does that make sense, everybody? Would you guys agree? If 3 is equal to 3, then 3 plus 7 equals 3 plus 7? Does that make sense? That by itself, my hopes are you would say, well, that's trivial. That's elementary. That's basic, common sense type thing, right? But that is one of the most useful properties that propels all of mathematics, okay? Every equation you've ever solved, did you do that? If I had 2x minus 3 equals 10. 2x minus 3 equals 10. You got a left-hand side and a right-hand side, and we're saying they're equal to each other. So your A in this case would be 2x minus 3. Your B would be 10. Does that make sense? Did you add 3 to both sides of that equation to solve it last year? Does that make sense? Added 3 to the left, added 3 to the right, and that would give you 2x equals 13, which is now also a valid statement. It's true, okay? And that exists. Every equation that we work through, for the most part, is going to have that process involved, and that property being used, okay? That's the addition property of equality. Now, we have another property that is very similar to it. The subtraction property of equality says essentially if you start with something that is true, two things that are equal, so if 3 equals 3, then 3 minus 4 is equal to 3 minus 4. Do you guys agree with that? I don't know. Hopefully that makes sense, because if you remember back to hopefully Mrs. Cole, Mr. McCoy, Mr. Hurd, whoever you had for math last year, explained to you that subtraction is adding the opposite, right? Okay? That's the definition of subtraction, adding the opposite. So subtraction is defined through the use of addition. So if we have the addition property of equality, we better have the subtraction property of equality. Okay? Because we can add the opposite to both sides. Does that make sense? Okay? Those things are what we use the most inside geometry. Those two properties are going to be very, very useful for us in geometry. And here's kind of where I want to take this to explain how we're going to use those two properties in geometry. Let me scroll over here to the side. I'm going to give you eventually 3 segments. So A, B, C, and D. And I'm going to tell you, the first step, I'm going to tell you, you know that AB's length is the same as CD's length. Okay? Now, understand, remember this from previous discussions, when I use this notation, there's a number that represents. There's a number that represents, right? Whatever that distance is, it might be 10 units, it might be 30 units, it might be 0.05 units. Whatever it is, AB is representing a number. Does that make sense? CD is representing a number. What is that expression right there telling you about those two numbers? They're the same, aren't they? Okay. Now, visually, by name or by the endpoints that we use, they're not the same. But quantity-wise, this distance here and that distance there are the same. So let's just say that blue distance and that blue distance are the same length, right? Well, what if I do this? What if I take that AB and I add to it BC, and I take my CD and I add to it BC. Do you see here in step 2 that it looks very similar to that step right there, does it not? You've got an AB on the left, you've got a CD on the right. Did I add the same thing to both sides? Okay. So what allows us to do that is the addition property of equality that says if A equals B, then A plus C equals B plus C. Okay. Now, here's where this becomes useful to us. If I look at AB plus BC, is that the same thing as that segment right there? Can I call that, instead of AB plus BC, can I call that AC? If I look at CD plus BC, is CD plus BC that segment right there? And instead of calling it CD plus BC, can I call it BD? Does that make sense? Okay. Is this a new fact that I didn't start with, but now I know to be true because I added the same thing to both sides? Does that make sense to everybody? Okay. Now, the reason that I can rename that as AC and BD is what we call the segment addition postulate. Okay. Or maybe we could even call it substitution. But now, instead, I started off with those two blue segments being equal. And now I know that those two red segments that I've got these braces attached to are also equal. And that's a new fact. Okay? And that's what geometry is about. That's what all of mathematics is about. Taking some small things that we know to be true, adding to it a couple properties, or recognizing a couple properties, and seeing that that spits out something new that is also true. Okay? So that's where we would maybe use something like the addition property of equality. Okay? Other than working inside algebraic equations like you did last year. Okay? We've got the multiplication property. So multiplication is defined as repetitive addition, right? So all that says is if I have A equals B, then A plus C plus C plus C would equal the same thing as B plus C plus C plus C. So if I add C to one side 3 times, I've got to add it to the second side 3 times, right? If I add to one side 5 times, I've got to add it to the right side 5 times, okay? So when we do repetitive addition, instead of writing like this first line up here, like plus C plus C plus C, we write as multiplication. A times C equals B times C. So as long as because the addition property of equality exists, and multiplication is the same thing as repetitive addition, the multiplication property of equality exists. Multiply both sides by the same thing, you get a true statement. Okay? Okay? We've talked about how, so this is all how math kind of intertwines. We've talked about how division is actually repetitive subtraction. Think about 8, and I want to divide it by 2. How many times is 8 divided by 2? 4. And that 4 comes from the fact that I take 8 and I can subtract 2 how many times before I get to 0? How many times do I have to subtract 2 from 8 to get to 0? 8 minus 2 will give me 6. Minus 2 again will give me 4. Minus 2 again will give me 2. Minus 2 again will give me 0, right? Subtracted 2 4 times. So division is repetitive subtraction. But subtraction is adding the opposite. So division is repetitively adding the opposite. Okay? So my hopes are that you see that subtraction, multiplication, division are all really versions of addition. Okay? So if the addition property of equality exists, those other properties of equality have to exist as well. The only thing that we have to be cautious of with division is that you can't divide by 0. And that's why they add that little C cannot be 0 there. We'll start with two sides that are equal. Divide both sides by the same thing. You should still end up with something that is equal. Okay? The next 3 are 3 that maybe you haven't seen before. Okay? I don't know if you have. You haven't really spent a whole lot of time discussing it. The first one is this. Like if I have 2x plus 3 equals 9, what would you guys do first to solve that? You put minus 3 there, and you'd put minus 3 there, right? Now, the reason you do this is because you understand the subtraction property quality, trying to keep the equation balanced. But what we should be really doing here, and nobody ever does this, no textbook really ever writes this or anything like that, or never any algebra teacher explains it this way. I explain it this way teaching my algebra because I know those kids are going to need this in geometry. But I should write that way. And that should make sense. I'm telling the person that's reading my work that yes, indeed, I know that I'm removing 3 from the left-hand side, and the 3 that I'm removing from the left-hand side is identical to the 3 that I'm removing from the right-hand side. Okay? When you make the argument that something is equal to itself, -3 is equal to -3, you're using what we call the reflexive property. Okay? It's a very simple property. It says A equals A. Okay? The way I remember it is reflexive sounds a lot like reflection, right? And if I'm looking in a mirror, my actual face is seeing my reflection is looking at my actual face. But there's 2 images there that are identical, isn't there? That kind of makes sense? Okay? If I look at A equals A, would you agree? So the equal sign is kind of the mirror? Is the left-hand side identical to the right-hand side? So one of those is my actual face, and one of those is the image in the mirror, right? Okay? So if you were to see something like 5 equals 5, or AB, whatever that length is the same as that length AB. Okay? Even though I don't know what AB is, I don't know what the value hidden behind that symbol is, I know it's equal to itself. Okay? It might not make a whole lot of sense. You might say, well, that's obvious. Anything is equal to itself. Yes, that's trivial again. You'll see eventually the purpose for needing to know that reflexive property. The symmetric property, where you guys have used that the most. You guys ever, Miss Coles was this way when I had her back in the 90s. If we had something like 3 minus 2x equals 5x, we would add 2x to both sides, and we would get 3 equals 7x, and then she would write it always as 7x equals 3. You guys do that? Always write your variable first. You don't have to, but what allows you to do this, okay, so this is an A equals B. So if A equals B, then B equals A. You're allowed to flip them because of the symmetric property. Okay? Does that make sense to everybody? Let me go back. You're allowed to take those things and any equation you ever come across, okay? And if you want to flip the sides, you can feel 100% confident in doing that because the symmetric property says you can. Is it necessary? Not always. Okay? When we work within proofs, generally speaking, the symmetric property doesn't get used very often. Okay? So it's kind of a second tier property with our proofs. But that's what the symmetric property is. The transitive property, on the other hand, is kind of that idea that I was using at the beginning with Landon and the Falcons. If A equals B, so if Atlanta beats the Eagles, and then B equals C, and then the Eagles beat the Lions, or whoever I said, then we can make the conclusion that the Falcons are going to beat the Lions. Does that make sense, everybody? If A equals B and B equals C, then A equals C. The way I like to visually, and we did this with the law of syllogism kind of, I like to write it this way. If A equals B and B equals C, then, okay, what I like to be able to do is take, oh, not that. If I take that and merge it down, do you see how the B's overlap? If A is the same as B, but B is the same as C, can't I make the jump from A to C? So I'm going to make that jump. And I'm going to say A is equal to C. Now what that does for us then, guys, I like doing that because you can kind of see kind of a middleman. Okay? B was part of both those equality statements, right? And if that B is that kind of linking middleman, let's just kick him out and relate A and C, because that should be true. The idea behind the transitive property, bare minimum, you need three things to be able to use the transitive property. I need three, football teams or whatever to make the transitive property. But the idea is I should be able to take a population of things. Could be three things, could be 300 things. As long as I know all of them are equal. So let's say I put all of you guys, let's just talk about your GPAs, okay? And I'm going to say all 20 of our GPAs are the same GPA. We all got 3.8. Can I take any two persons' GPAs and equate any of those two people? Does that make sense? Okay? That's what the transitive property allows us to do. Okay? Now, you might not, especially with equality, we might not make a whole lot of sense of its purpose right now. Okay? But the idea is you should be able to take as many objects as you want, as long as they all have that property of being the same, and then grab any two of them and relate any two of them the same way. Okay? So that's a transitive property. We use that one a lot. Okay? And the last one is the substitution property. Okay? And you guys have done the substitution property. You have, in algebra, if I have 2x plus 3y, and I ask you evaluate when x equals 5 and y equals 12. Didn't you guys last year say, oh, that's 2 times 5 plus 3 times 12? You took that object there and replaced it with what it was equal to, right? X was equal to 5. You took that thing there and you replaced it with what it was equal to, 12. That's all substitution is. If A equals B, then B can replace A in any expression we want to. So, an example of that, we said X was 5. So, 5 can replace X anywhere we need it to. Y was 12, so 12 can replace Y anywhere we need it to. Is that okay? Substitution is you're going to hear me say this over and over and over again. Replacing something with what it's equal to. Okay? If I'm a coach, the idea of making a substitution in a game, okay, is so that I can take somebody out and replace them with somebody of equal ability, right? That's the hope. Now, it doesn't happen all the time in athletics, but the idea is that I'm replacing somebody to do the same thing that the person I took out was doing. Okay? So, all right, everybody? So when I replace that X with 5, that 5 is doing the same thing the X was doing. If we were to kind of list these as a hierarchy of the ones that are going to use the most, I would say the transitive property is number 1. You're going to use that the most throughout all the proofs that we do. And you don't need to write this, but that would be number 1. Transitive property would be number 2. Okay? Reflexive property 3. These two properties would be 4. We don't use the multiplication, division, or the symmetric property that often. Okay? They pop up every once in a while, but those are the properties that we're going to use almost every single proof. Each one of those will show up in it, especially early on. All right, so those are properties of equality, because remember, equality is talking about numerical values being equal to one another. Okay? The next category of properties are properties of congruence. I know I skipped a couple, we'll go back. But properties of congruence. You see here we have, again, the reflexive property. We have the symmetric property, and we have the transitive property. All we need to think about, though, here, so they're the same linking procedures as what we saw in properties of equality. So reflexive property was the idea that we've got a reflection. The left-hand side is exactly the same as the right-hand side. Okay? But now, because it's congruence, we're thinking shapes. So if I were to give you any segment, you could take any segment, cut and paste it, and land it on top of itself, right? That make sense? So what that's saying is that any segment is congruent to itself. Again, something pretty obvious. Any angle is congruent to itself. Again, pretty obvious. But as we start doing proofs and we start introducing some algebra inside our proofs, those are going to be very important properties for us. Okay? We learn them here in Chapter 2 with the reflexive property, and we're going to use it in Chapter 2. We use it in Chapter 3. But you really won't recognize a true need for the reflexive property until we get to Chapter 4. Okay? But we will use it as we progress to Chapter 4, just to get in that habit of seeing it being used. Okay? Seeing it being present. Symmetric property just says, if I've got a segment in my left hand and it's congruent to the segment on my right hand, I can then say that the segment in my right hand is also congruent to the segment in my left hand. Okay, you can read equality statements and, in this case, congruency statements, left to right or right to left. Okay? And then the transitive property just says if I've got a bag full of congruent segments, and I know they're all congruent, I should be able to pull in to that bag and pick any two out and compare any two of them and be congruent, right? Okay? You guys ever do any construction? Anybody ever built a wall before? You built a wall, Landon. Huh? Like you've built a wall at home with Dad, drywall, that kind of stuff? You've never done that? Come on. Alright, so like if you were to tear the drywall off of your wall at home, guys, you're going to see these things right here. Hunter, what do we call these things? I'm asking you for a reason, Hunter. What do we call these 2x4s that are behind our drywall at home? Hunter, I'm asking you for a reason, man. Those are called studs. Okay? But they're just 2x4s that are usually about 8 feet. Okay? But let's say maybe we go buy you can buy 2x4s in all kinds of different measurements. But let's say that we go and buy 9-foot 2x4s. But the wall that I need is 8 foot. Okay? Can I go through and take all my 2x4s and just cut them all off at 8 and just create a big pile of 2x4s? And then just grab any one of them and put the first one here, second one there, second one there, second one there. Does it matter which 2x4 goes there first? Not if my pile has got them all being the same length, right? That's the idea of the transitive property. I've got a pile of distances. A 2x4 is just a segment, right? I've got a pile of segments. I know I cut them all 8 feet long. Okay? So it doesn't matter when I make this wall. It doesn't matter which one goes first, which one goes second, which one goes third. They're all 8 feet long. Does that make sense? Okay? So that might be kind of an application that we've seen, or maybe that you use with 2x4s. Okay? Or sorry, with the transitive property. You guys never know. Do they still have a class in middle school where like industrial tech or anything like that? No, that's it. When I was like 5th grade, I was building walls with Mr. Goff. Like during school. You guys don't do that? Man, you guys are getting cheated.
I mean, I have like my stepdad did a project in the house, and I got to like hit a drywall with a hammer. It was like the greatest thing.
What are you gonna find? Because I think that's an application, guys, that all of us at some point in our life are going to encounter. We are either ourselves going to maybe work on our home, or have maybe our significant other work on our home, okay? And you're going to recognize maybe some of these geometric properties kind of existing as you do those things. The distributive property, you guys used this a lot last year, right? Distributive property, fancy word for what? Fancy word for what operation? When I take that A, and I do that with it right there, and I get AB, what am I really doing? Multiplication, isn't it? When we say distribute, it's a fancy word for multiply, and it actually means to multiply repetitively, right? Okay? So we got this idea that addition and multiplication are linked. Multiplication defined as repetitive addition, distributive kind of repetitive multiplication. Okay, so there's links here with these ideas. And you guys know that you've done that before. Okay, the one thing I want to talk about here is that we can actually apply the distributive property backwards. If I have AB plus AC, what term do they both have here? Do they both have a term of A in them? Okay. Now, in order to find out what's left over in these two spots, do you guys remember what you did last year? If you were taking A out, didn't you try to divide that by A and see what you're left with? What's going to happen with those A's? They cancel, right? What are you left with? B, correct? Divide that by A. Those cancel. What are you left with? Plus C, right? Okay? So the idea here is that when I start with something like this and I recognize that they both have an A in them, and I can pull that A out, and now I have a number times a B plus C is just going to be a number, right? Okay? And let's think about this. A times B is a number. A times C is a number. A number plus a number is just a number, right? Does that make sense? Now here's the idea, and I wrote this on purpose this way, and I know this might be kind of confusing at first. But I've got a number on the left-hand side, and now I say it's equal to two numbers being multiplied. So if I had like a number like 8 on the left-hand side, the right-hand side would look like 2 times 4. Does that make sense? Or if I had 15 on the left-hand side, the right-hand side would be 3 times 5. What is the process called when I take 15 and I rewrite it as 3 times 5? Or 15 is called the product, right? What are the two things that we multiply together to get the product? What would 3 and 5 be called? Starts with an F. Factors, right? So that's what we did right here, right? If I have AB plus AC and I write it this way, so this is my product, I just broke it apart into its two factors, correct? Okay? Now, if you think about the process that we went through, all we did is we took AB and divided it by A, and AC and divided it by A. So factoring is a fancy word for division, isn't it? Okay? So distribute, fancy word for multiplication. Factor, fancy word for repetitive division, essentially. Okay? But the reason I talk about that is because in your homework you're going to see something like this. 2x plus 3x. And they're going to say that line somehow is maybe given information. And they want you in the next line, what are you going to rewrite that as? You're going to write that as 5x, aren't you? Using our algebra skills from last year. Anybody remember what you called that last year? Y 2x plus 3x is equal to 5x. What if I gave you this acronym? Combine like terms. You guys agree with that? Okay. Here's the thing. When we do this stuff in our homework tonight, there's going to be drop-down windows. Okay. And tomorrow and the next day, there's going to be drop-down windows. And you're going to provide a reason. And in that drop-down window, when they go from 2x plus 3x and it gives me 5x, and you get to tell me the reason why it's 5x, combine like terms is not going to be an option. You guys know why combine like terms works? If I have 2x plus 3x, what do they both have in common? X. Can I pull that out and get that? What's 2 plus 3? 5, right? I have x times 5. Don't we generally rewrite that as 5 times x? Okay. So, the reason why we combine like terms like that is because of essentially the factoring procedure. But they're not even going to call it factoring. They're going to call this the distributive property. which it really is. If I take x times the quantity 2 plus 3, it should give me 2x plus 3x, and I can add that as 5x. So whenever you see what you think, and this might be something, this is kind of the thing that I do with, I know you guys are writing my notes kind of like I had them written here, but to make them your own, maybe you write here on the side, combine like terms for homework equals distributive property, okay? And that will help you. So we will see that a handful of times in the next couple of days. Eventually, once you see it enough, you're going to realize, combined like terms is the same thing as distributive property. Is that okay? Combined like terms is a phrase that educators, math educators, have come up with that allows kind of a quick way for students to kind of understand and realize what they're supposed to be doing. And that's kind of what I hate about math, is that educators at some point, way before me, and I didn't have any input in this, they start writing textbooks and they start using these phrases that help people do the work, but those phrases kind of circumvent why they're doing the work. It doesn't explain, why 2x plus 3x is really 5x. Okay? I'm going to skip over some of this stuff. It's just an explanation of that. Okay? So if you download my PowerPoints, this slide will be in there. It's just an explanation of what we just talked about. So I don't want to do that again. We've already done this one. Okay, we've already talked about the transitive property. So we'll skip that a little bit. This is going to be what your homework's like. Okay, and this first assignment, guys, is going to be very kind of the one property at a time type of approach per question. Okay, when we start doing proofs eventually, it'll be like 6 of these things together inside one question. But in your homework tonight, they're going to tell you that this first step is given. So we're going to assume that this is true. There's no debate. There's no argument. We're saying this is what we're starting with. They're going to ask you then, what is the reasoning for you to be able to go from the first step to the second step? So what happened from the first step to the second step? What they do to both sides? They subtract 9 from both sides. So your reason will be the subtraction property of equality. Subtraction property of equality. At this stage, we're not so interested in us being able to do the algebra. We're interested in what allows us to do the algebra. Why could we do that? So we're allowed to subtract the same thing from both sides. Does that make sense? Okay. Part B here. Okay. So what we're using here, guys, is the law of detachment and the law of syllogism really to make these statements. Okay. This one is going to be given. Okay. Now think about this. We had some phrases earlier that said if an angle A is congruent to angle B and angle B is congruent to angle C, okay, then we could say this first one was congruent to the last one, right? Is that the same thing we got going on here? O to W, but W goes to L, so can I make the jump from O straight to L? You guys remember, so we've got a match here. Okay, this second rectangle here is a match to a true hypothesis. So this is the law of detachment. And then we say, okay, if this is true, then what conclusion can I make? I can make angle O congruent to angle L, right? Anybody know why? What's that property? When I have a bag full of things that are all congruent, and I can reach in and pull 2 of them out and say that those 2 are congruent. Is this an A equals B and B equals C statement, and then this is A equals C? Is that the transitive property? Okay, now just be careful. Because in your drop-down windows tonight, there's going to be a transitive property of equality, and there's going to be a transitive property of congruence right underneath it. And if you just see the word transitive and click the first one you see, you might be wrong. So make sure you know that it's property of congruency. How do I determine that? Well, I look at the picture, I look at the words, the phrasing, and it's got a congruent symbol in there, right? Okay, if I had an equal sign, I'd use transitive property equality. What allowed us to flip things? What allows me to flip that equation? This first step is given. What allows me to just make these things kind of spin? What allowed us to do this? Maybe if I write it this way, if measure of angle E equals measure of angle T, then measure of angle T equals measure of angle E. That's kind of what we're saying here. If then was a line right down the middle, kind of like the line right down the middle of your body. Does your left-hand side of your body match your right-hand side, correct? If I make that line go right through the word then, and I fold, does measure of angle T fall on measure of angle T? Does measure of angle E fall on measure of angle E? So that's the property of symmetry, okay? So this is a symmetric property of equality. Just flipping the sides. Don't do anything else, but just flip the sides. You get a symmetric property of equality, okay? Symmetric property of, we still got 5 minutes, guys. Don't be packing yet. What do we got here? Symmetric property of congruence. What are we doing here on B? Distributive property. Okay. So all these first lines again are still your given. Okay. What do we do with C? First line is given, but then how do I go to x equals 28? What'd you do to both sides? Okay, division. You divided by a fourth, right? Anybody multiply by 4? So there's 2 reasons. There's 2 arguments of why that would be true. So if you say division, that's fine. You say multiplication, that's fine. Usually when there's options, they're going to tell you, what did you divide? They're going to ask you, what did you divide by or what did you multiply by? Okay? This last one says measure of angle R equals measure of angle R. The left-hand side is identical to the right-hand side, right? Anybody remember what that's called? Reflexive. Good. Okay? And it's equality, so reflexive property equality. All right? So, what we're going to do, guys, we're going to start proofs tomorrow. Okay? I'm just going to introduce what a proof is right now to you. It's an argument. Okay? It's a convincing argument using deductive reasoning, so using facts and properties and theorems and definitions that we already have shown to be true. Okay? To make the argument about something new. Okay? The idea of this is that we cannot have gaps. Okay? Let's say Hunter robs a convenience store, or let's say not robs it, but is being charged for robbing. He's in court, and I'm his lawyer. I'm his defendant. Okay? And I could tell you everything that would kind of justify that he did not do the crime. Okay? Well, let's say the crime was done at 2:30 p.m., and I can't tell you where he was at 2:30 p.m. on the day of the crime. Would that be a gap in my argument? Yes. So when we do proofs, there might be 6, 7 steps. But if are you missing one of those steps, that's a gap in the proof, and then somebody can attack that. Okay? So we don't want that to happen. Okay? A proof is a logically developed argument of why something is true. Okay? And what that basically means is if statement D is going to be true, it's because we have verified and shown that the statements A, B, and C that came before it were true first. Okay? Does that make sense? Okay? A final statement can only be true if the things that happened before it were true. Okay? The Falcons are only going to beat the Eagles if the things before we talked about at the beginning of class happened. Does that make sense? Okay? We can only make that argument if the things prior were also true. So tomorrow I will print off the next series of notes for you. Okay? Working with proofs can be a tedious process with a lot of writing, so I'll try to minimize that for you as much as we can. So I got some printouts for you tomorrow.
Hmm?